All right, so I will speak about some class of flexible polyhedral surfaces, about algebraic problem that arises from that, and about the solution of that problem using elliptic functions, and then about some other geometric items. So, so this will be again polyhedral surfaces which should not be flexible, but they are. So that's similar to Jan's talk. This time they will not be closed. What I'm looking at is a polyhedral surface which is made out of quadrilaterals that are connected by hinges, and the surface has the combinatorics of the square grid. So like in the upper right corner here. Of course, if you take just the usual squares, I mean the really Euclidean squares, then you can bend this surface by folding it along vertical lines or folding it along the horizontal lines, and this is not interesting. If you take a random surface, then you will not be able to fold it. And because of that, it is interesting to study those configurations, so those geometries which lead to flexible surfaces. One famous example is the Miura-Ori fold, which is shown here on the right bottom. So this is a surface that flexes, and it has numerous applications in engineering and even space industry. There are other classes of flexible surfaces described so almost 100 years ago, and but the question of characterization of all these surfaces was open until recently. So if you look at just a small part of the surface, namely at the neighborhood of one face, so I take any of the quadrilaterals and take somehow its small neighborhood, then it is possible to show that if the neighborhoods of all faces are flexible, then the whole surface is also flexible. So let us look only at this small polyhedron made of 5 quadrilaterals and 4 triangles, and let us ask ourselves when can it be deformed. And so this page shows an example of a flexible Kokotsakis polyhedron. So there is a central quadrilateral face. So this is the bottom face that you cannot see here. And then 4 quadrilaterals on its sides and 4 quadrilaterals on its corners. And this surface is flexible. I know it, I had it in my office. It is flexible because, so by symmetry reasons. So let us look at how can we try to solve that problem. So here again on the bottom left, you see Kokotsakis polyhedron. So let us look at any vertex, any interior vertex of that polyhedron. Let us take a small sphere centered at that vertex and intersect the sphere with the polyhedron. Then what you get is a spherical quadrilateral, now pictured on the bottom right. So its sides are arcs of great circles, and the side lengths are equal to the angle, so to the angles of our polyhedron. And the angles of that spherical polyhedron are equal to the dihedral angles of the, I mean, the angles of spherical quadrilateral are equal to the dihedral angles of the polyhedron. And also, of course, such a tetrahedral angle, so an angle with 4 faces, it can be flexed. And this corresponds to a deformation of the spherical quadrilateral, which preserves the side lengths. So there's exactly one parameter family of motions of this quadrilateral. But our Kokotsakis polyhedron has 4 interior vertices, and these 4 vertices must deform in some compatible way. So we must look at 4 spherical quadrilaterals and see what compatibility conditions, or what dependencies are there between them. Let us first look at 2 vertices. So take 2 spheres, look at the corresponding spherical quadrilaterals, and then you find out that they share an angle. So this the dihedral angle at this edge is a common angle of the 2 quadrilaterals. So we can put them in this way and form a scissors linkage. So this is a pattern joint framework, but with one special vertex. At this vertex, you have 2-digit bars which are connected in the middle, and so they can move exactly like scissors do. It is also possible to realize it as a classical pattern joint framework. So for that, one has to put some additional bars, but that's not the subject here. So we have this scissors. This still has one parameter family of deformations, but we must continue to other vertices, and then we get 4 quadrilaterals which are connected consecutively as scissors. And if you put this all on the same sphere, then this chain does not necessarily close. It's not a problem, it does not close, but the deformation, yes, and this chain has exactly one parameter family of deformations. If you deform one of these quadrilaterals, then all the other, they will follow you. And the condition that the Euclidean polyhedron can flex, this condition is equivalent to this one parameter family. I mean, this is equivalent to the condition that when this spherical framework deforms, then the 2 marked angles are always equal, because they correspond to the same dihedral angle in the polyhedron. So that's some non-trivial condition. We have a one parameter deformation, and we also want from this one parameter family that the angles are equal. All right, so how can we approach that? Let us write some equations, some formulas. Let us take again an individual spherical quadrilateral with side lengths alpha, beta, gamma, delta, and denote by phi and psi 2 of the angles of that quadrilateral, so 2 adjacent angles. So this spherical quadrilateral can deform with 1 degree of freedom, and this means that the angles phi and psi are not independent. There must be some equation connecting them, and this equation can be written down by using spherical trigonometry. Namely, if we denote by z and w the cotangents of halves of those angles, so that's the usual substitution, then you get a polynomial equation. And now if we look at our spherical linkage, so this pattern joint framework, and mark these 4 angles, so these are 4 angles because these 2 angles must be equal, then we get 4 polynomial equations. So this is, so to say, a cycle. So this system has a cyclic structure. The first polynomial depends on Z1, Z2, the second on Z2, Z3, the third involves Z3, Z4, and then finally Z4, Z1. And the flexibility condition is that this system of 4 equations and 4 variables has a 1 parameter family of solutions, which is, of course, which happens only in exceptional cases. So we must characterize all those configurations when the system has a lot of solutions. Now, of course, it's interesting what exactly these polynomials look like. And they look like as follows. Again, so z and w are cotangents of half angles. Each of these polynomials is a polynomial of degree 4, but where both z and w enter only in second degree. Also, there are not all terms somehow. There is no z squared w, for example. So that's quite nice looking equation. The coefficients of that equation, they can be expressed in terms of the side lengths by these nice formulas. So as you can see, there are all possible combinations of plus and minus signs. So before beta, gamma, and delta, and it also means that if your quadrilateral is somehow special, for example, yes, for example, alpha plus beta plus gamma plus delta is equal to 2 pi, means that the corresponding vertex is intrinsically flat, because alpha, beta, and gamma, and delta, these are these angles, alpha, beta, gamma, delta. So if their sum is equal to 2 pi, then it means that this vertex can be flattened in the plane. And if if alpha plus beta plus gamma plus delta is equal to 2 pi, then the term C0 vanishes, right? But I'm now more interested in the most generic case, so where there are no dependencies between alpha, beta, gamma, delta. So we have a equation of degree 4 like this. And in total, we have a system of 4 equations like that. And yes, and that's actually, well, that's a system of real polynomials, and we are interested in real solution sets. But so it turned out that, at least in my approach, to solve this problem, so I had to use complex analysis. So I had to I complexified the problem. So I asked, when does this system has a 1 parameter family of solutions in the complex domain? If you solve that, then of course you are left with another problem. You must understand when your complex solutions are actually real. But so let us discuss only the first problem. So how to describe the when this system has a 1 parameter family of solutions. So it turns out that elliptic functions can be of use here, because let us take first a simple equation like this. It's very similar to what we had, but there is no term of z squared times w squared. And for this equation, well, of course, it's a curve of degree 2, so that's a conic section. And more exactly, that's that will be actually a hyperbola, because well, I mean, in my case, it will be a hyperbola because I know that C20 and C02 have opposite signs. But so that would be an ellipse and hyperbola, and centered at 0. So it's really symmetric with respect to 0. And one can easily show that this curve can be parameterized by trigonometric functions like that. So that sine t and sine shifted by some phase t0, and also some amplitudes p and q. Now, in our equation, there is this additional term, z squared w squared. And it turns out that this curve can also be parameterized by either by elliptic sine or by elliptic cosine. So whether you must take sine or cosine, it depends on the so it depends on some, I mean, depends on the coefficients, of course. It also depends on the shape of the quadrilateral. In fact, so it depends on whether you can turn inside out your quadrilateral by continuous deformation, by isometric deformation. All right. So this means that for every quadrilateral, its configuration space, so by which I mean the space of quadrilaterals with fixed edge lengths. So this configuration space is an elliptic curve, so which is in complex domains and topologically a torus. And let us now look again at our polynomial system. We have 4 equations in 4 variables. We can, in fact, build a diagram of blanched covers. So each CP1 here, it is the domain of the tangent of half of the angle. So tangent of half of the angle is a point in CP1, and Z12 is the configuration space of a quadrilateral. So actually, this Z12 is the solution set of the equation P12 Z1 Z2 is equal to 0. And of course, so this solution set projects to the domain of Z1, and it also projects to the domain of Z2. These are 2 arrows here. And then we have also 3 other configuration spaces. And we have a 1 parameter family of solutions if and only if this diagram commutes. Now, what does it mean to commute if there is no closed cycle along the arrows here? So it commutes in the following sense that each of these projections, it is a twofold planched cover, and we can consider the inverse like a multiply valued function. So if you can go, so if you can climb the arrows, so climb some arrows and follow the other arrows and come back, and this solution extends to the whole CP1, then well, actually not to CP1, but to some cover of CP1, then we have a 1 parameter family of deformations. All right, and then the approach is to study more complicated configuration spaces, namely over Z12 and Z23, you can construct the fiber product, so which is then the configuration space of 2 adjacent quadrilaterals, and then rise up and up to the big configuration space, and then analyze, at some point you have to analyze the monotony of these punched covers and see that some cases are excluded. So the problem consists in analyzing, in classifying all flexible cases. So in particular, you have to show that there are no other cases, right? As those that you have described. All right. So anyway, this is again a picture of what happens with these branched covers. So these tori are the spaces Z12, Z23, and so on. So here, this is the domain of the variable Z1, the domain of Z2. And this is that 5-bit product, which is a branched cover then over both of these tori. And so this approach also resembles a bit the approach of Litt, who analyzed the decomposition of polynomials as compositions of polynomials. For example, one can ask when two polynomials commute if you use the composition as the operation. And so he solved this problem exactly by considering branched covers and the monotonies of branched covers. So I cannot provide the details here now, but I just mentioned that at some point one has also to look at the monotony there. Good, and finally, this leads to this approach led to success, and it also allows to describe some classes of flexible Kokotsakis polyhedra using elliptic functions. Namely, there is a class where the dihedral angles are parameterized as it is written on this picture. So P1 times the elliptic sine of t. This is Z1, and this is Z2, Z3, Z4. And so remember that Z1 is actually the cotangent of half the angle. So it's not really the angle. So that's one of the classes of flexible polyhedra. And as next, I think I go over to the third part of my talk. So namely four-bar linkages. Because in the process of studying this problem, I stumbled upon some very interesting facts, so theorems that were actually proved in the 19th century, but then they were forgotten and rediscovered again by several people. So here's a fun geometric problem. Now I take a quadrilateral, not a spherical quadrilateral, but just a usual quadrilateral in the plane. So this is this gray quadrilateral, and I fold it along one of the diagonals. So let me denote by I an operation on quadrilaterals which fold them along this diagonal. What does it mean, this diagonal? I consider quadrilaterals with two fixed vertices. So these two bottom vertices, they are pinned down on the plane, and the other two are arbitrary. And then on this space of quadrilateral, I can consider the map I, which is folding along the right diagonal, and the map J, which is the folding along the left diagonal. Now let us start with any quadrilateral and repeat these foldings. First J, then I, then again J, then again I, and so on. And let us ask ourselves what happens with this quadrilateral after several foldings. So let us make some experiments. Here is an arbitrary quadrilateral, and I'm folding it once, twice, and so on, and so on. It turns out that after about 50 iterations, you get this picture. So here the iterations of foldings, they are dense in the configuration space of the quadrilateral. So the configuration space, again, it's the space of all isometric deformations of this quadrilateral. This is a one-dimensional space, and these foldings, they reach every point of that configuration space. Reach every point on distance epsilon. Let us now take another quadrilateral, this one, and let us make foldings 1, 2, 3, 4, 5, 6, and that's the same. Well, if you didn't fold, then let us fold back. I claim that after 6 foldings, this quadrilateral becomes again, so returns to its initial form. So remember what it looks like, and let us do 1, 2, 3, 4, 5, 6. That's it again. So that means this is the whole orbit of the folding. And what is interesting about it is that whether or not the quadrilateral returns to its original shape, it depends only on the side length of the quadrilateral. So here on the top and on the bottom, I have two quadrilaterals with the same side length, and on the right are the orbits of the folding. So in particular, it means that if I deform my quadrilateral, then the picture on the right also deforms. So it's a deformable linkage, deformable bottom joint framework. And this is a paradoxical mobility because this framework has more edges. So it has so many edges that it should not be flexible. It should be rigid. And again, but for some particular edge lengths, they can be flexible, and so they are by the theorem that I just stated. This theorem was proved by Darboux many years ago. So it says exactly what I just claimed. If a quadrilateral has folding period n, then all quadrilaterals with the same side length have folding period n. And I want to say that after what I presented in the first half of the talk, the proof is easy. So let us look at this picture again. So this is a quadrilateral with side lengths alpha, beta, gamma, delta. Never mind if that was a spherical quadrilateral or Euclidean one, everything works the same. So for this quadrilateral, there is the I folding and the J folding. The I folding preserves the angle Z, and the J folding preserves the angle W. Now we know that in the configuration space of the quadrilateral, Z and W are parameterized by the elliptic function and its shift, right? Then what does the I folding do in terms of the parameter of the parameterization? The I folding should preserve Z, and what map does preserve Z? It's the map that sends T to 2k minus T. So it's similar to the trigonometry, in fact. So if 2k is equal to pi and your sine is the usual sine, then it's the sine of pi minus T is equal to sine T. And elliptic functions have similar periodicity properties. And the J folding, it preserves W, and therefore it must have this form. But then the composition I of J of T is T plus 2 tau. This means that, so this composition is simply a shift in the configuration space. And the folding of this quadrilateral is n periodic if and only if 2 tau times n is a period of the elliptic sign. But then the folding is n periodic independently of the shape of the quadrilateral. I mean, if you keep the side length but change the shape, then if it was periodic, it remains periodic. All right, so that's the story about Darboux's theorem. And as I said, actually it was unfortunately forgotten, this work, and then we discovered several times. Then one can ask, well, we know that the periodicity depends only on the side length. So what is the condition that an ABCD quadrilateral has folding period 2? So that it folds after IJ. It is not difficult to prove, and so you can do it in your spare time, that if this condition is satisfied, then this quadrilateral has folding period 2. It is more difficult, so really more difficult to show that if AC is equal to BD, so the products of the opposite sides are equal, then the period is again 2, but after IJ, actually the quadrilateral changes its orientation. So how about an arbitrary n? So when does a quadrilateral has period n? So the quadrilateral that I have shown on the previous pictures, it has this nice lengths, 3 square root of 5, 3, 1, and 5. This is one of the solutions of this equation, and this equation tells you when the folding period is 3. There is a general formula for any n. So let us take, so A, B, C, D are the edge lengths of the quadrilateral. It's denoted by capital delta AC plus BD, by small delta AC minus BD, and by delta bar this expression. Well, just the expressions that jump into your mind. Then take this polynomial of degree 3, take its square root and write down the Taylor expansion of this square root. You get a sequence of numbers. Then a quadrilateral with these side lengths ABCD is n-periodic up to orientation if and only if this determinant vanishes. So there are two conditions. One holds for, if n is odd, and the other one is the condition if n is even. So probably you have heard about Poncelet Buddhism. This is also a similar statement that if you start at some point and you close, then you will close starting from any other point. And closing conditions for Poncelet, they have similar form. So these are Cayley conditions. And so the proof of this theorem actually uses, well, it can be proved by the same method as Cayley's condition. Good. Then, in fact, it is not easy to see in these formulas, so they are not very intuitive on the first sight. But if you make a certain operation on the numbers a, b, c, d, namely if you replace a by minus a plus b plus c plus d half, and similarly for b, c, and d, so then you get 4 new numbers, and if you use them as the side lengths of the quadrilateral, then then it turns out that these new numbers, they satisfy the following equations. For example, so this AC plus BD, this was the capital delta. So if you make that operation, then the capital delta does not change, and small delta and small delta bar, they are exchanged. Delta becomes delta bar becomes delta. But this means that if the ABCD quadrilateral is n-periodic, then A bar, B bar, C bar, D bar quadrilateral is also n-periodic. So that's something absolutely mysterious on the first sight. And the proof that I just gave, it's a purely algebraic proof without any geometry, which is not very satisfactory maybe. That is luckily also geometric proof. So this duality, it is based on the Ivory's lemma about net of confocal conics. And also later we found out that this is actually a special case of another very nice theorem, that is duality for tetrahedra. Right, so that's the folding of quadrilateral, and I finish by another very nice geometric fact, which turns out to be connected to what I spoke about. So this is the so-called zigzag Buddhism. Let us take 2 circles, and let us choose a length L. Then, so draw a segment of length L with one endpoint on one circle and the other endpoint on the other circle. Now fix one of these points. So let's say fix the point on the small circle. Then the other endpoint, there are 2 positions for the other endpoint. So here is the second position. So then let us construct a polygon, a zigzag, by jumping between these 2 circles. So from this point, I again draw a segment of length L to another point on the small circle. From there, again, a segment to the big circle, again to the small circle, and here I have come to back to my initial position. And a theorem by Bottema says that if this zigzag closes after 2 n steps, then it closes independently on the initial choice of the point. If I start with any other point on the big circle, then again this chain will close. And so some people have noticed that this actually corresponds to the folding of the quadrilateral, because so we have in this problem we have 4 numbers. One number is the radius of the small circle, the other number is the radius of the big circle, the third number is the distance between the centers, and the fourth number is the fixed length L, the length of the segment. And so this red quadrilateral is one that you have seen before, so with these edge lengths, and constructing the zigzag actually corresponds to folding the quadrilateral. So this time the small side of quadrilateral remains fixed and the other edges, the other vertices jump.